In video games, real-time fluids can be a tricky topic. Personally, we have always been fascinated by this kind of simulation. Today, we will create a real-time liquid on Unity. When you speak about liquids, fluids, soft bodies or metaballs, they are often associated with techniques such as Raymarching or MarchingCubes. With the name MarchingCubes, we also enclose MarchingSquares, Marching Tetrahedra or DualConturing. In this project we want to use a different approach inspired by the work of Nvidia. Of course, we divided this approach into two parts, the simulation and the rendering. The simulation consists in giving a fluid the correct behavior. Basically, we are creating rules that say act like a fluid. Rendering, on the other hand, consists of recreating the fluid from an aesthetic point of view. This time we are saying you must look like a fluid. The simulation is an implementation of position-based particles, and the rendering is done in screen space. The implementation of the simulation could be particularly difficult and tedious, as it involves many mathematical and physics concepts. We did it based on the paper by McLean and Mueller from Nvidia. The whole implementation is based on compute shaders. This allows us to use the GPU to instantiate large quantities of particles. Given the complexity and the specificity of the topic, we would like to ask you to tell us if you want a dedicated video or maybe a small series about it. In today's video we will focus on the rendering part. As we said, the fluid surface is rendered in screen space. This is because we use the position-based particle and so we have no meshes or grids. Only the particles, the position and their density. Of course, this does not exclude the techniques mentioned at the beginning of the video, but they could become very expensive. For instance, using MarchingCubes, the bounds of the liquid affect the size of the grid of cubes and therefore the performance. The basic concept is to use the camera point of view and compose the surface through different information levels. These levels are generated by specific shaders that use buffers to write the results. Once the result is being inserted in a buffer, they will be available for another shader to process them, and so on until the desired look is achieved. The steps we have performed are generating the depth of particles, smoothing the depth, calculating the normals, calculating the thickness of particles, and shading the surface. To each step corresponds a dedicated shader. The first thing we did was to use a geometry shader to create a code for each particle. Then in the fragment shader we calculated the normal and the depth. Also we distorted the pixel outside the circle. Once we got the depth texture, we had to blur it. We did it by using a bilateral filter instead of Gaussian blur to preserve the edges. The problem is that the bilateral filter wouldn't be separable, but we need to separate it into steps, horizontal and vertical, in order to preserve the performance. So we forced the separation into steps and ignored the artifacts because the shading phase will cover them. At this point we used the blurred depth and calculated the normal. To do that we used the two tangent vectors and then calculated their cross product. For the thickness we rendered the particle again using a geometry shader to generate the quads. Then we use a Gaussian splat and reuse the bilateral blur on the result. All these steps allowed us using the latest shader to obtain a convincing surface for our liquid. Here we used the depth value to divide the liquid from the background, and calculated all the usual characteristics such as diffuse, ambient, specular, etc. We also calculated the Fresnel and inserted a cube map to enhance the reflection on the edges. Using the Beer-Lambert's law, we get the color variation related to the amount of the absorbed light. And using the thickness value, we adapted the transparency. As a final touch, we added the texture for the caustic and generated the foam. The latter has been calculated using the velocity of the individual particles. Particles with a higher value will tend to the white color. The cool thing is that we can apply this technique to any group of particles we want. Either it is made on the GPU, as in our case, or it is a classic GPU particle system. This rendering approach was presented by Nvidia at the GDC 2010. Let us know in a comment below what you think about this project and if you want us to go deeper on the simulation. Don't forget to subscribe, smash the like button and follow us on the other socials. See you next time. Cheers!